All right, so far we've assumed that the solutions can be fractional. And in the example that we had, about the marketing example, we had fractions 1.82, we had 3.81, and then 10. So the TV and the radio, there were decimals of the decision variables. An integer is a positive and a negative whole number. So none of them was a whole number. But non-integer solutions are not allowed in practical life. Why? Because, for example, if you are buying aircraft, you can't have 38.56 aircrafts. Neither can you be able to produce 400.18 vehicles. So there are certain things that are not decimals, and you can't have them decimals. How do you handle with that? Integers will do the magic. So sometimes the temptation is to round off. So instead of 48.53, the person will just round it up to 49. Now, rounding off has its own problems. Okay? It can affect profit, it can affect loss, it can yield suboptimal solutions, it can even cause infeasibility. Okay? I'll give you an example. Let's say that you round off something that is 20.83, and then you round it up to 21. But what you didn't know is that the 20.83 is 20 billion point 830 million. So by rounding it up, you've made a big mistake by taking a huge, amount which shouldn't be taken. So we need an integer optimal solution. Now, what this integer optimal solution does is that it's the same as the other one. It's the same as the linear programming problem. The only thing is that you need some condition. In addition to the non-negativity constraint, you need an integrality constraint. The integrality constraint in Excel is called int, integer. Sometimes you need bin, binary. You need that. Okay. So an integrality constraint will tell you that all of the decision variables are not just non-negative. They are not just 0 or positive, but they are whole numbers. They are whole numbers. Okay. Unlike variables that are not required to assume strictly integer values, okay, they are called continuous variables. So continuous variables have got decimals. So there are 3 types of the integer program. 3 of them. The first one is total. The next one is binary. Okay. So the total is where all the variables are integers. They are not just non-negative, they are integers. Then we have a situation where the variables are 0, 1, 0, 1, 0, 1, 0, 1. Okay. And then we have a situation where you have a mix of some of them are integers, some of them are whole numbers, and some of them are also decimals. Okay, so that's the mixed one. So what we are going to do is that we're going to learn how to formulate them, but you should try and solve them in Excel on your own. But one of them will try and do it in Excel. So let's learn the formulation of an integer programming problem, first of all. All right. So there are quite a number of examples. Let's take this particular example on the screen. Agbala, owner of a machine shop, is planning to expand by buying some new machines, presses, and lathes. So the company is preparing to buy presses and lathes. These are used in producing items. Each press that they buy will increase profit by 1,000 cedis every day. Each lathe will increase profit by 150 daily. And the number of machines Agbala can buy is limited. It's limited by the cost of the machines and the available floor space. So the variables, you can see that for this formulation are the cost constraint and then the floor space constraint. The machine bought, their prices and their spaces are all going to be shown here, okay, below here. So you think about how to formulate the decision variable. So these are the equations. So each press requires a floor space of 15 and a purchase price of 8,000. That is for each floor space. Now each lathe requires a floor space of 30 feet square, and the purchase price is 4,000. Now Abdullah has a budget 40,000 for buying the machines, and in terms of the square feet too, there are only 200 square feet available for the floor. The guy wants to know how many of each type of machine to buy to maximize the daily increase in profit. Formulate an integer linear program. Formulate an integer programming problem. Now, of course, I have already told you at the top there that is a pure integer. So it means that you know in your head. But if I had not told you, you got to be able to think about how that is possible. So let's go to the story and indicate the decision variables. How are we going to indicate the decision variables? Okay, the decision variables, how do you write them? Okay, let this x1 be equal to something, let x2 be equal to something. Now, these formulations are skills that you already know, so it's going to be very, very fast, okay, in the way we go about it. So the x1 will be the number of presses, okay, to produce or to buy, and then the x2 will be the number of lathes to buy. Okay. So the number of presses, and it's always good to learn how to write this, because, and of course, it must come with a unit of measurement. That's why we have the number. Okay. And then this becomes the number of lathes. What is going to be our decision variable? Now, when you look at the storyline very carefully, you will notice the decision variables were mentioned right there in the story. Watch it. It says that each press will increase by 100 each, 100 profits, and then of course each lathe will increase by 150 every day. So the decision variable is going to be what? Sorry, the objective function is a maximization. So you do z max, okay, equals to 100 x1 plus 150 x2. That's your decision variable, subject to the constraint. What were the constraints? Well, you notice that there were two kinds of constraints that were given. Constraint number one was a floor constraint. Constraint number two was a purchase price constraint. And then the purchase price, there's a budget limit of what? 40,000. And the floor, there's a budget limit of 200 square feet available. All of these indicate that there is a less than or equal to sign. So let's do the floor one. The floor one, we need 15 of the x1, the press, plus 30 of the x2, the lathe. So 15 plus 30. Okay, so you have 15 x1 plus 30 x2 less than or equal to, and then you will have your what do you call it, your 200 square feet, because this is the floor, 200 square feet. And then you have the other one, which is the budget constraint. The budget constraint was 8,000 and 4,000. So you write 8,000 x1 plus 4,000 x2 less or equal to 40,000 was the budget limit. 40,000. And then we need your non-negativity constraint, which is x1, comma, x2, comma. It says that it's non-negative. But we know that all of these are integers. So how do you add that part to indicate that they are integers? Simple. You can just do comma, x1, x2, then you just add integer. That's it. Or after this, you just do comma and just write and integer. And integer. That's that's it. You've done the formulation and you are sorted. So you just indicated that the whole thing should be an integer situation. So that's it. Finish. We'll let you can do the formulation in Excel later on. Let's go to another example. Another example, which is a little bit trickier because this one is a 0-1 example. And it's not that simple. So follow me and focus. Follow me and focus. Legon Council must decide which of the 4 recreational facilities to build. The word must decide is an important word. Decide to build. That's the key. You got to decide to build. Now they have to choose among pool, tennis center, athletic field, gymnasium in such a way as to maximize the daily usage. So you are maximizing the daily usage by residents. Now the expected daily usage, the costs, the land requirement for each of the projects are below. And by the way, let's show that first. Okay. So the expected usage per day is this. So we are expecting how many people to use a swimming pool a day? 300. We're expecting 300 people to use the swimming pool every day. We're expecting 90 people to use the tennis every day. We're expecting 400 people to use the athletic field. And finally, we're expecting 150 people to use the gymnasium every day. Now, if 300 people use the swimming pool, that will cost us to produce 35,000 swimming pool if we want to build up. And it requires 4 acres of land. It requires 4 acres of land. So these are like the requirements, but the very first one is the usage. So that will go into the decision variable, whereas these ones go into the others. So what are the limitations? What are the available for the ones that will go into the constraints? Well, if you look at it, the Legon Council has $120,000 of budget. 12 acres of land available. So that's the other part. But there are some restrictions here, which is where it becomes a little bit technical. But if you think, you will crack it. Because swimming pool and tennis must be built. Keep that in mind. Okay, swimming pool and tennis must be built on the same part of land parcel. Only one of these two can be built. The word can and must are important, okay? Because swimming pool and tennis must be built on the same part of land, okay? So you can't go and build swimming pool and tennis separately. They got to be built on the same, but because of that, you got to also choose only one of them to do. We'll analyze that. The company want to know which facility to construct. That's important. They want to know which facility to construct in order to maximize the expected daily usage by a resident. Okay. They wanted to know which facility to construct. So let's go to the storyline and then try and make sense of this whole scenario. Let's get a page. Okay. What do you think is going to be our decision variables? What do you think is going to be our decision variable? What do you think is going to be our decision variables? And if you like, I can take you back here. What do you think will be the decision variables? Well, okay, so the decision variable will be construction of any of the facilities. Because you got to decide, which facility to construct. So if I am deciding on to do swimming pool, then the possibility is that I am not going to build something. Okay, I'm not going to build a gymnasium. I'm going to build something. So the possibility of some particular facility being built, it becomes a binary choice. Either you got to be built or you are not being built. Okay, and so the way you will have to write the decision variable will be let x1 be the construction of a swimming pool. Okay, because that was the first thing to handle, the construction of a swimming pool. The next one was tennis center, then athletic field, then gymnasium. So let x2 be the construction of a tennis center, x3 be the construction of athletic field, that's x3. x4 becomes the construction of a gymnasium. The construction of it, okay, the construction of it is a very, very important. So we let that represent the very, very situation. And of course, you need to write your objective function. The objective function based on what we just looked at. But first, you need to understand whether this is what kind of integer programming. Is it pure or not? Well, if you look at each one of them has a possibility of being built or not being built. And so because of that, okay, these decision variables are binary choices of a linear programming. So they become a binary integer programming that you're going to do. Now, please note, something can be a whole number but not binary. You can have a whole number but not binary. And it can be mixed with something else that is binary. So in this context, these decision variables, because each project can have values of either 1 if it is selected for construction, or 0 if it is not selected for construction. Okay. Right. Now let me take you back to the information that we have. So now we are going to formulate our objective. And according to the objectives, we are maximizing the expected daily usage. This one. So the coefficient for each decision variable is going to be these values. So how do we do that? Well, let's go to see how we formulate it. So we are going to start with what? Z max. Let me see whether there's a question someone has. Okay, I'm now going to write this. So if you don't see, don't worry, I'm now going to write it. So let me show you. You have Z max. See whether you can see now. Z max equal to, okay. Then,
yes, I can see.
All right, let's move on. Z max equal to, and watch it here, 300 x1 plus 90 x2 plus 400 x3 plus 150 x4. So that's what we're going to write there. So you have 300 x1 plus 90 x2, 300 x1 plus 90 x2 plus 400 x3 plus 150 x4. This is our objective function, subject to the constraint. Okay. And as you may remember, if you check the graph there, let me just go back to the graph. If you check the graph there, you see that there are two constraints first. You have the cost or the budget constraint, and you have the land constraint. Okay. Land constraint. The cost constraint, we are going to add all of this. And then the land constraint, we are going to add all of this, each multiplying the very decision variable. But look at the limit. You are told that the limit for the budget is 120,000. Okay. That's 120,000. Then the limit for the land is 12 acres. Okay. So we just put that down. Let me just put that down first. Okay. So you have 120,000 on the right hand side. You have 12 acres on the other side. So we can now take our budgetary amount and then fix them there. So that's going to be 35, 10, 25, 90. Okay. 35, 10, 25, 90. So you have 35,000 x1. Okay, 10,000 x2, 35,000, 10,000, 25, 20. Let me just delete this. Plus 25,000 x3 plus 90,000 x4. So all of this should be less than or equal to 120,000. Then the cost, sorry, the acre of land, we have 4273. 4273. So just write that for the acres of land. 4273. Then you bring the plus. That's for x1, x2, x3, x4. So now you've been able to execute all of the two main constraints that were given there. Okay. But there was something else. There was something which is known as a contingency constraint. Now I'm going to go back to the analysis and show you. There was a contingency constraint. I want to show you this. So look at it. It says that because swimming pool and tennis must be built on the same land, only one of these can be built. Okay. That's a contingency constraint. That's a contingency constraint. So how do we capture that? Okay. How do we capture that? Because these two, tennis and swimming pool, must be built on the same land, okay, because they gotta be built on the same land, only one of them can go onto the land. Now remember, it says that either the swimming pool, which is the x1, or the tennis, which is the x2. Okay, so watch it carefully. It says either the swimming pool here, which is the x1. Let me use a different color for this. This is interesting. Either the swimming pool, which is the x1, or the tennis, which is the x2. Either of them, okay, and that word, either this or, the word or means plus. So keep that in mind. Either of this can be built. That's what I said. Can be built, but not both. Now let's try to understand this principle. Either can be built, but not both. This is an important thing. Either can. Now, if something can be built, what does that mean? Can. If I can build it, then it means I'm making it come to life. Okay, either of them can be built. So I am making it come to life. And for the thing to come to life, it is a binary choice. For the thing to be constructed, it is a binary choice. All right? For the thing to be constructed, that is a binary choice. And because that's a binary choice, it will be given a value of what? Because it's a binary choice. Can be built. Okay? So it means that it will be given a value of what? In our context, if you are going to be built, or if you can be built, you'll be given a value of what? A value of what? Because you have only two choices. The first choice is you being constructed, which is a value of what? 1. And you not being constructed, which is a value of what? 0. And so if you are going to be built, you'll be given a value of what? 1. So that is it. So you write 1. But the word is can, not must. So first, let me put a 1 here. Okay, let me put a 1 there. Let me put a 1 there. But it was can, not must. If it must be built, that is what symbol. And if it can be built, that's what symbol. Okay. If it must be built, then it means by all means it gotta be what? 1. If it can be built, then that will be what? Can means that if it was must, it would be what? Equal to sign. Equal to. But this is not can be built. Sorry, if it was must, it would be equal to. But this one is can. So can means that you may or may not be built. You may or may not be built. So that is less than or equal to. Of course, less than or equal to 1. The less than the 1 will mean that you were not built because you have only two choices, 0 or 1. The less than means you are not going to be built. But the equal to 1 means you have been built. So that is a can. Now let me take you back. And then it says that both, but not both. Okay, that is a can, but not both. Let me see if I can take you back to the storyline to help you here. Storyline to help you here. It says that a tennis center must be built on the same land of the parcel. Because swimming pool and tennis center must be built on the same land, only one of these can, only one can be built. But look at the first word, because both, okay, because either swimming pool or tennis must be built. Now that means that each of them has a possibility of being built. And so tennis is what? X1. Tennis, swimming pool is X1 and tennis is X2. So each of them has a possibility. And because each of them has a possibility of being built, and it is either one of them going to be built, the word either this or that is a plus symbol. Either this or that is plus. Either or. Now if you have done a little bit of mathematics, you know that or means plus. Okay, or means plus. So you just incorporate that into the analysis and then you add them. So we go here, it's going to be x1 or, which is plus, x2 less than or equal to 1. That is what it means. 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 So the summation of them. So this is mutually exclusive constraint. Let me show you up here. So this is a mutually exclusive constraint. Mutually exclusive constraint. Okay. So if one is going to be built, then the other one cannot be built. They are mutually exclusive. Let me ask you some questions here. What if it has rather said that either swimming pool or tennis center must be built but not both? What if it has been like that? Either swimming pool or tennis must be built but not both. What constraint would that be? There's no question you will know the constraint, isn't it? What symbol is that? Okay. What constraint would that be? What symbol would that be? Okay. Either swimming pool or tennis must be built but not both. How would that be like? Okay. It is going to be, let me see whether somebody has written it. Somebody has written it. Let me see whether it's correct. Okay. So Michael said x1 equals to 1 or x2 equals to 1. No. Okay. Remember there's or, which means that we got to add something. You got to add. Okay. So because you got to add, the way it has to go will be what? It will be x1 plus x2 equal to 1. I said this before. Okay. Okay. So that one forces 1 for not being built at all. Forces 1 for not being built at all. Yeah, I think the others have been able to catch up the scenario and how it's supposed to be. So that is it. Oops. That is how it's supposed to be. So you now let me show you that in the slide. So that is called multiple choice constraint. Multiple choice constraint. Okay. So you have no choice. If you choose this one, you can't choose. So you are forcing one to choose the other. Now, of course, there's a non-negativity constraint which has to be there. And this is a non-negativity constraint. Now, this, we know that from here, either is every variable has a choice of being built or not. So it is a binary constraint. So the way you write it is this: x1, x2, x3 equal to 0 or 1. That's it. Equal to 0 or 1. That is a binary constraint. Equal to 0 or 1. That is a binary constraint. Of course, you got to bring your non-negativity constraint, which doesn't nullify this constraint. The non-negativity constraint is greater or equal to 0. That's still there. But this is a binary constraint. built in. Okay. Now let me ask you some constraints. What would these constraints look like? Suppose you have exactly 2 of the 4 projects must be built. Exactly 2. Exactly 2. That word exactly means equal to, by the way. Exactly 2 of the 4 must be built. Exactly 2 of the 4 must be built. How would you have written it? Exactly 2 of the 4 must be built. And remember, now we know that the final value of each of these projects has to be 0 or 1. Okay. So the maximum value of an x1 can be is 1, and the maximum value an x2 can be is 1, because it's either 0 or 1. So exactly 2 of the 4 projects must be built. How would that have been? Exactly 2 of the 4. Okay. So this is going to be what? Exactly 2 means equal to 2. Okay, let me see an answer somebody has given first of all. Equal to 2. Yeah, that's a perfect answer. Okay. So that means you have x1. Okay. It means that you have x1 plus x2 plus x3 plus x4 equal to what? 2. That's what I mean by exactly 2. So you have to appreciate the entire situation in there, and this is exactly what you have there. So your ability to be able to formulate these constraints are important. Of course, that's not what is in the story, but if that had been the case, what if you had, so in this case, no more than 2 of the projects must be built. Oh, that's a constraint. What if you have had this constraint, no more than 2 of the projects must be built? What symbol is that? No more than 2. No more than 2. What symbol is that, by the way? No more than 2 is what? Excellent answers I'm getting here. Less than or equal to Michael. That's good. Okay, less than or equal to. So no more than 2 of the project. So the whole thing is here, x1, x2, blah, 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 less or equal to 2. That's it. Okay. Now what if you had this one? If swimming pool x1 is very important, oh, very important. Remember, I didn't say it's the best, but I said very important. And tennis center is less important. So swimming pool is very important. Tennis is less important. What does this constraint mean? How will you have written? Okay. So swimming pool is more important than tennis. That's what it means. How would it have written it? X1 is more important than X2. X1 is more important than X2. How would that be? Okay. X1 is more important than X2. Okay. But if X1 is more important than X2, okay, there's a limit to which X2 can be. So let me see the sign. There's a limit to which X2 can be. Yeah, that's good. But check your signs. Okay, check your sign. You are right with the linking of the X1 and X2, but the sign is very important. See, when I say more important, so I say very important. Very important. I didn't say more important. I said very important. This is said to be a conditional constraint. This means that the tennis center has no chance of being selected if you are selecting the swimming pool. Okay. If you are selecting the swimming pool. So it has to be x1 greater or equal to 2. x1 greater or equal to 2. Now the temptation will be, of course, x1 greater or equal to 2 is the same as x2 less or equal to 1. Oh, sorry. It's x1 greater than 2. Is x1 greater than 2, which makes it x2 less or equal to 1. Okay, which makes it x2 less than equal to 1. And I think you got it, Michael, or somebody, you got it. Okay, so that's a conditional constraint. Let's go to the last one, co-requisite constraint. What if swimming pool should be built if and only if tennis must be built, and vice versa? Swimming pool should be built if and only if tennis must be built, and vice versa. This one is easy. Okay, equality sign. Okay. So one cannot be built without the other being built. So they are the same. They are the same. They are the same. They are the same. Okay. By the way, this is our original constraint. Complete model that you see there. Okay. This is all that we dealt with. Beautiful. Beautiful, beautiful. So this becomes our integer constraint. Now let's take the very last one. The very last one. Of course, this is the last one, and this is mixed integer. So it means that some of them will be binary. The possibility is that some of them will be binary, some of them will be non-negative, some of them will be continuous decimals, some of them might or will be, whole numbers. So you would have to identify which is which. Nancy has $250,000 available for investing in building land bonds. Now, building, land, bonds. Which one is likely to be decimals? Building, land, bonds. And this will generate greatest return after 1 year. Each building costs $50,000 per unit. Okay? And that will lead to $9,000 profit if sold after a year. Each land costs $12,000 per acre. And that will give you $1,005 profit per year. Bonds cost $8,000 per bond. That will yield $1,000 profit per year after you sell it after 1 year. Now, these ones are simple. The main one is this: only 4 buildings, 5 acres of land, 20 bonds are available. So that is on the right-hand side of the constraint. Formulate a mixed integer programming problem. Now, even if you have not been told to formulate a mixed integer programming problem, you will know that some of these things are integers. They gotta be whole numbers. They got to be whole numbers. So the question you have to ask yourself is this: let me just go back here. I don't want you to quickly get the answers to this. I want you to think through the answers. Okay. Of course, what will be your decision variable? Remember, what will be your decision variables? Let me take you back here. Let me see some of the answers that you have. Okay. If I take you back to the storyline, okay, Nancy has $250,000. So what will be your decision variables for investment? So that's going to be amount invested. Okay. Amount invested in building. Amount invested in land, amount invested in bonds. Or you can say building investment, land investment, bond investment, or buildings bought, lands bought, and then bonds bought. That would be your decision variables. Let me just write that, because some people, if you don't write that, so let's X1 be buildings bought. Let X2 be land bought. Let X3 be bonds bought. So these are your decision variables. Okay. Now, what to be the objective function? What to be the objective function? Let's just go back. Okay. Look at this last sentence. Formulate the integer programming. But you see, you are going to do an investment to make, and then say that will generate the greatest return. Return. Okay. And each year, the cost here and then the profit. The profit is more or less the return. 9,000, 1,005, 1,000. Okay, 9,000, 1,005, 1. Okay, so what will be your, let me just go to the next page. What will be your Z-max? What will be your Z-max? Who has a trial? You can raise a hand and tell me the possible Z-max that one can have. Which ones are we having? How would the Z-max be like? I can show you the screen if you want me to show you the screen. I can show you the screen. Who can raise a hand and tell me what the Z-max is? Okay, somebody is even documented that beautifully. Okay, so the Z-max is going to be 9,000 x1, 1,005 x2, 1,000 x3. That's how it's going to be, because those are the profits or the returns. Okay. So this is going to be 9,000. 1005 and then 1000. Okay. X1, X2, X3. So this is your Z max, and of course subject to certain constraint. The first constraint you can remember is the budget. Okay, that's the budget. Let's go to the storyline and then you look at it. That's the budget. If you look at it, it says that 50,000. Okay, the building will cost 50,000, the land will cost 12,000, and then the bonds will cost 8,000. But then all of these, you have $250,000 available. Okay. So these three added together with their decision variable should equal that $250,000. So you have to just fit in the values. Okay. The first one will be what? 50,000 x1 plus the second one was giving us 12,000 x2, then the last one was giving us 8,000 x3, and all of this should be less or equal to $250,000. So this is your first constraint, which is a budget constraint. Okay. Now there was something in the question that can also help us to understand some few things. He told us the availables. Let's go to the question. It says that bonds, okay, it says only 4 buildings, 5 acres of land, 20 bonds are available. Only 4 buildings. Buildings is X1. So it will be X1 less or equal to what? 4. 15 is the land. So it will be X2 less or equal to 15. And then the last one will be X3 less or equal to 20 because of the word available. So let's add that constraint individually. This one you don't add them because it didn't say or. Okay. So you go here, you do x1, okay, which is what? 4. Okay. Then x2. X2 was giving us 15. So you do less of x2 less or equal to 15. Then x3 less or equal to, I think that was 7, right? Yeah, or 20 bonds. 20 bonds. So you're done with the formulation, but you are left with some few things. So now we need to decide which ones are non-negative and which ones are non-negative. Which ones are non-negative and which ones are not non-negative. Which ones are non-negative? We know that when you are non-negative, you can be an integer or you can be a binary. So which ones are, negative and which ones are not non-negative? Now this is where you just have to think. Now look at X1. X1 was what? Buildings. Can buildings be decimals? Buildings, can it be decimals? Because buildings cannot be decimals, buildings will be an integer. Okay. The next one is land. Can land be decimals? Absolutely. There's no question about that. Land can be decimals. So we can say for sure, write it here that x1. Okay, let me just document that. Okay. We can just write it here that x1, x2, which is the land. As for that, it has to be greater or equal to 0. Non-negative, without indicating that it's an integer. Okay. But we know that building will be what? Decimals. Okay. Buildings cannot be decimals. So that is that. Bonds, can it be decimals? Somebody has already written the answer for that. Decimal, somebody say, how can land be decimal? Oh, you can have a plot of a land. You can have one and a half of the land. You can have 1 plot of a land. You can have a quarter plot of a land. You can have 2 plots. You can have 2.5 plots. You can have 3 plots. You can have 3.5 plots. You can have 3 1/4 plots. You know we do that. So land, you can cut them, you know it. You can cut pieces of the land and then make the land. You can have, sometimes we even speak of square feet, okay? 2 by 4 square feet of land, okay? We can have them even in square feet, in yards. You know, we can have them in decimals. Does it make sense? Excellent. So as for land, you can have them in decimals. It can't be a whole number. Now land, you can have, you know, 1.5 of a land, a building. This is my building. How many buildings you have? I have 2.5 buildings. What is that? It doesn't make sense. So land is a whole number. Building is a whole number, but land can be decimal. Bonds is also a whole number. Okay, bonds, once you get a bond paper, it's also a whole number. Okay, so the land is in decimals, but the x1, which is the building, and then the x3, which is the bonds, these are not just greater or equal to 0, but you have to indicate that they are also integers. So you add and integer. Okay, you add and integer for those ones. So those are non-negative. The fact that it's 0 greater or equal to 0 means it's non-negative. But if you want to prove that they are integers, you add and integer. There's no binary here. There's no binary. There's nothing that may be there or may not be there. And so that settles it. Ladies and gentlemen, these are the different kinds of, you know, integer linear formulations that you can have, you know, every time. Okay, every time. Let me just take you back to the. So those are the things. Any question? Any question?